Hi there and welcome to this video for Senior Physics on Electromagnetism and Electricity. In this video we're going to explore resistors. Now some of this will be revision for you, but basically it's a good idea to have an understanding how resistors work into our circuits so that we can incorporate them with our capacitors and our diodes for use in this topic. Well, first off, a resistor is simply something which is going to slow down or speed up the amount of current which is able to flow through a circuit. Now often these are as simple as having different types of metal wires. Different metals will conduct electricity at different amounts. Now obviously the more tightly compact the atoms are in the metal, the slower the electrons will pass through, which means they offer up more resistance. Now resistance can be changed by increasing the length of a wire, or it can be changed by changing the thickness of the wire. Now basically in a circuit, resistors are often in the form as you can see in the diagram here. There's specific resistors which are set up which give up a specific resistance, and that size of resistance is basically shown by coloured banding patterns which appear on the outside, as you can see in the two diagrams on the right hand side. Now in these two diagrams you can see that both of them have different colours and there are 4 bands. So what we're going to do is just very quickly run through how do we determine the size of the resistor that we're dealing with using these bands. Now at school at St Hilda's this will not be assessed, it's more of a case of familiarity. However, if it is going to be assessed in your program of study, then this will also help you understand what's going on. Generally you would be given some of the information because there's a huge amount that you would have to remember. So basically the first band, and let's look at the top diagram. The first band basically is just a value, it's a number value. Now you can see there on the top right hand diagram we've got a brown band to start off with. So you go to the middle table which is surrounded in red and find brown, and you write down number 1. That's its ohmic value, that's one of the numbers that makes up the resistor. The second colour band in this case is black. Now black is 0, so we would write down 0. So now we've got brown is 1 and black is 0, so we get a value of 10. Okay, so the third band, and in this case you can see it's the blue band. The blue band basically will denote, because it's in its third position, it will denote the number of zeros you add to those two numbers. So remember we've got 1 for the first band, 0 for the second band, and then if we look on our table we can see that blue is 6. So basically what we would have is 10 and then 6 zeros after it, which basically is 10 million ohms or 10 mega ohms. Now the fourth band, often in this case is gold, it can be silver or there can be none at all, talks about the tolerance. Now the tolerance is measured in the form of a percentage, and all the tolerance basically does is tells us how accurate that ohmic value is. So remember we said that we had 10 mega ohms. Now in this case it's got a gold band, which means it's got a 5% tolerance. So the 5% tolerance basically means it's 5% above or below, or positive or minus, of that 10 mega ohms. So 5% is quite a small region, which means it's very close to 10 mega ohms, which means if you want a specific resistor, that one is one that you can use. There are smaller ones which will go down to things like 1%. Obviously if you went up to a 20%, that means that a fifth of it, it's very unreliable. So if you're wanting a resistor that's got a huge range, it doesn't really matter, then you can put that in and that will be fine. But if you want a specific value, then you want your tolerance number to actually increase. Now obviously if you've got 5 bands in your resistor, then basically the first 3 bands, as you can see in the notes there, the third band is also a value as well. So you would just add up your first 3 values, your fourth value would be the number of zeros, and then your fifth band would basically denote your tolerance. Okay, so let's have a quick go and see if we can work out what the value is. Okay, so here I've got a resistor. It's got a red band, followed by a red band, followed by a green band, followed by a silver band. If you pause the video now, try and work out what your ohmic value is of your resistor. Okay, so welcome back, and let's see how you got on. So for the first band, we look in our middle table and we can see that it's the number 2. So we'll write down number 2. The second band is also red, so we'll write down number 2 there. So those are my two values because I've only got 4 bands. So it's 22. Now I'm going to work out the number of zeros that come after that. Well, it's green. Green means that there are 5 zeros that come after it, which means so it's 22 plus 5 zeros. So basically that puts it at 2,200,000 ohms. Now it's also got a silver band. Now if I look in the third table, silver basically means I've got a 10% tolerance. So it's 2,200,000 ohms plus or minus 10% of this value. So it could be anywhere between 10% above 2,200,000 or 10% below 2,200,000. So that's the range of my resistance for my resistor. So as you can see here, that's how we would write it, or I can put it as 2.2 mega ohms plus or minus 10%. Okay, so there are two main types of resistors that we tend to have. We have variable resistors and potential dividers. Well, this is how they can be used. Now basically a variable resistor is where we can alternate the amount of resistance that goes through the resistor. So we can change it as we move through. Now sometimes you'll see this in a laboratory where you've got a rheostat. Rheostat consists of a large lump of coil. Current comes in on one side, it goes through the coil, and then you'll have a spreader bar at the top, which will allow you to determine how far along the wire your current is going to go before it comes out and goes into your next appliance. Now, basically, if you look at the diagram here, current enters through A, it will then go round the loop and then come out at B, and it can go all the way through and come out at C if we wished it to. Now, basically what we can do by turning the wiper along the track, what that means is the further to the right I turn my wiper, the more the current has to go through the wire, the more energy is lost, and as a result, more resistance is put up, which means I'm going to get less energy coming out at B. However, if I move the wiper more towards B, more to the left-hand side, it means the current coming through A, there's less of wire to go through, less energy is lost, which means more energy is going to come out at B. Now this works really nicely in things like volume control or in a dimmer switch. And in this case, you can see a situation where we've set up here. Now on a dimmer switch, what you do, you have a certain amount of energy going through to your light bulb. However, when you turn your dimmer switch, you can either turn the light bright or you can turn it so it's dim. Now if it's going to be dim, you'll move your wiper more to the right hand side, which means more current is going to go through the resistor. It will lose energy, which means there's going to be less energy coming out through your light bulb, which means it's dim. However, if you want your light bulb to be bright, you move your wiper more to the left, which means less current will go through your resistor, which means more energy will come out, so your light is bright. This works equally as well as I say with a volume control, but it's in reverse. In this case, if you want your volume to be high, we always turn it up to the right being high. We'd have to switch our resistor around. But basically what that would mean is if we want it really high, we want the current only to pass through a small amount of the resistor. However, if we want the sound to be low, we want it to pass through more of the resistor, so it loses more energy. Okay, well I hope that makes sense. The other form of it is a potential divider. Now this works really well when you look at something like a car radio. Now a car battery works off 12 volts, but a car radio will only work off 6 volts. Now if we put 12 volts through our car radio, it won't work and it will blow up some of the components. That's not good, especially if you spend a lot of money on your car radio. So what happens is that within the circuit we put a resistor, and that resistor basically will get rid of 6 volts. It will use up 6 volts of energy as it passes from the battery, goes through the resistor. 6 volts of energy, or 6 joules per coulomb of energy, will be lost as it passes through the resistor, which only leaves 6 volts going into the car stereo. Then in the car stereo there'll be a variable resistor on your output control for your volume, and the result is you can then use your wiper on your volume to basically say whether I'm going to get 6 volts of energy coming out as sound, i.e. it will be high, or we diminish it. So if I wanted 6 volts, I'd move B to position X, very little comes through the resistor. However, I want a very quiet sound, then I'd move it to Z. And if I wanted a very mid sound, I'd move B to Y, which would mean only maybe 3 volts is coming out through my output. Okay, so I hope that makes sense, and hopefully you understand how we can utilize our resistors to control what's going on inside our circuit. Now, as well as understanding this, we also have to calculate some of the things. So let's just run through some simple algorithms that we can utilize for resistance. Well, the first one is what happens when we've got a resistor in series. Now, if we've got a resistors in series, we basically look at what's the resistance of the total circuit. Now, remember, series is where we've got all the resistors in a loop. So what we do there is we add our resistors together. So we basically convert the 2 resistors, 3, 4 resistors in the loop to as if they're all just one big resistor. So R tot or R total will equal the R1, the resistance of the first resistor, plus the resistance of the second resistor, and so on and so forth until we've dealt with them all. That's basically like saying, well, I've just got one big resistor and the current will flow as steady current all the way through. Now for parallel, it works in the opposite way where we work on the reciprocal. So we've got R1 branching into R2, branching into R3, 4, 5, etc., etc. In this case, we use the reciprocal rule. 1 over R total will equal 1 over the resistance in R1 plus 1 over the resistance in R2 plus 1 over the resistance in the next branch, and so forth and so on. Key thing to understand here, solve the right hand side first, turn it into one simple fraction, then flip both sides or do the inverse to both sides, and the result is you'll get R total. What I often find with students is they do 1 over R tot and they add together 1 over R1 plus 1 over R2, and then they say that the resistance is that 1 over R1 plus 2. It's not right. You must inverse first before you do it in order to get R total. Now, some other electrical algorithms, just to refresh your memory, is we've got V equals IR, where V is going to be the voltage, I is the current, and R is the resistance. I'm sure you learnt that earlier, probably in your middle school years. You've also got I equals Q over T, where I is going to be the current in amps, Q is the charge in coulombs, and T is the time in seconds. Okay, so let's have a look at a simple resistance scenario. We've got 3 resistors in series, and we've got a 12 volt DC supply coming out. We've got an ammeter going in series, as they always are, and then we're looking at AB, BC, and CD, what the voltage is across each of the resistors. So basically, the first question asks us the current drawn from the 12 volt supply is registered on the ammeter. We've got to calculate what it is. We've got to calculate the value of the voltages VAB, VBC, VCD, and then we've also got to work out what would be the appropriate connection for a 3 volt for 3 volts of a 10 milliamp motor. So first off, let's have a look. Well, we've got to work out our total resistance. Now, our total resistance, because all the resistors are in series, in order to find out our current, we add all our resistors together. So we get R1 plus R2 plus R3 is going to equal 79 ohms. So when we put it all together, we get 79 ohms. We know that our voltage supply is 12 volts, so we use V equals IR, and we get 12 divided by 79, means that we get 150 milliamps flowing through our circuit. Now, this 150 milliamps is going to be useful because there's going to be 150 milliamps flowing through each of our resistors. So we know our resistors and we know our current for each of our resistors because it's always going to be the same. So in order to calculate B, which is the resistor, the voltage between AB, BC and CD, it's literally going to be using VA equals IR. And in this case, for VAB, we're going to get the voltage across AB is going to be I times R1. Well, we know 150 milliamps times 10, so we get 1.5 volts. For the voltage across B and C, we've got I times R2. Well, it's 150 milliamps times 22, which is 3.3 volts. And for the voltage between C and D, it's the current times the resistance in R3, which is 150 milliamps times 47, which is 7 volts. And the final question asks us to talk about what would be the appropriate position to place a 10 milliamp um, motor which is working on 3 volts. Well, the best one's going to be VBC because it's 3.3 volts. So you're going to get maximum output there. You can't put it through AB because you're only giving out 1.5 volts, and 7 volts is too big. So 3.3 volts will be just about enough to go through a 3 volt motor. The current doesn't matter there because it's 10 milliamps. Okay, the overall current is a lot larger. So as you can see there. So I hope you found that this resistance video has been useful to you. I do look forward to you joining me again. Our next videos we'll start looking at capacitance. Okay, so I look forward to you joining me then. Thanks for watching.